So back in the main GUI, after we've just processed the spec data, we can press the Load Patient button to refresh the latest data that we've acquired. And now we see in this spec another data panel in the table, there's now a spec time point at about 5 hours after injection. So we can go back into our regions that we've analyzed, and if we choose the left kidney, now we see the planar data that we had before, and now we have an activity of 25 megabecquerels and a volume of about 128 mils that we got from the SPECT analysis. And we got this using a 40% threshold. Something else we acquired in the SPECT GUI were these thicknesses of the left kidney and of the patient at the level of the left kidney. And as I mentioned, these thicknesses are used in the conjugate view method to correct the planar data by subtracting the background counts. So the method for actually doing that is described in mirrored pamphlet 16, but here all we need to do is just click this update thicknesses / perform background correction button, and our activities will now be corrected for background in the planar data. Now we're ready to actually calculate our time integrated activity coefficient using the hybrid planar spec method. So in the TAC processing radio button box, we just need to make sure that the hybrid planar spec radio button is selected. We can use a multi-exponential. This will default to just a mono exponential fit through the data. And we're ready to just perform fit and calculate time integrated activity. This gives us our time integrated activity coefficient, and we can now just store that for later use in the organ level dose calculation. We can do the same thing for the tumor. Again, we have these thicknesses. We just don't want to forget to update the planar data, so recalculate these activities using the thicknesses for background correction. Again, these are the activities we got from the SPECT GUI, so that was 55 megabecquerels in the tumor, a volume of about 61 mils. And we just perform fit and calculate the time integrated activity, and we get a time integrated activity coefficient of about 1, and we can store that in the database. If we want to see the time activity curve that we actually get from this fit, we can just press the plot TAC button. So this is the time activity curve that we get. And well, one thing you might want to do is try to fit a bi-exponential fit through that. Maybe a curve that starts at 0, 0, and using a bi-exponential. So in our fit type, under multi-exponential, we can choose the fit options button. And in the window that comes up, we can change the number of terms in our exponential to 2. And we can include the point 0, 0. Press OK. And now when we perform the fit and calculate the time integrated activity coefficient, we get a slightly different value. Now we're losing some of the area under the time activity curve because we're starting from 0, 0. We can see what that looks like in the time activity curve. And that's our new time activity curve. We can take a look at what, first we should store that time integrated activity coefficient. We can again take a look at the left kidney. And if we plot that time activity curve, it's a more reasonable fit using a mono exponential. Now another function of the main GUI that I'd like to point out is, suppose you have a case where here you've used technetium-99m as your injected radionuclide, but you want to use this injection to predict the time-integrated activity coefficient of a therapeutic radionuclide, assuming that that radionuclide is part of some radiopharmaceutical that will follow the same biodistribution as your injected radiopharmaceutical. So in this replace radionuclide panel down at the bottom, here we have iodine 131, but actually we have a longer list of different replacement radionuclides that we could choose. Let's go with lutetium 177. There's the corresponding half-life for lutetium 177. This is what's going to be used in combination with the biological half-life, which you get out of this effective half-life from the technetium injection, and with an updated effective half-life for lutetium, we can calculate a replacement time-integrated activity coefficient. So this is the time-integrated activity coefficient of the left kidney, assuming that a lutetium 177 labeled radiopharmaceutical is following the same biodistribution as our actual injected radiopharmaceutical. And we can just store that value. Once we have a complete list of all organs of interest in our investigated organs here, we can go on to do a organ level dose calculation. We get that from the procedure menu in this calculate dose option. And in other videos, I'll also demonstrate how we can use the process spec data GUI, which we've already seen. And I'll show how we can use that to calculate a 3D dose distribution using either the voxel S value technique or Monte Carlo simulation.